Today we're going to provide an example combining both qualitative and quantitative explanatory variables. In the past, we talked about these two topics separately, but today we will see how actually you can combine those two separate topics within the context of a single linear regression model. Today, it's an example combining both qualitative and quantitative explanatory variables within the context of the same example. So, example, combining qualitative and quantitative explanatory variables. So that's kind of the general topic. So, generally, so what we are talking about, so let's say, assume that we have two explanatory variables. Let's say that x1 is a qualitative factor, or represents qualitative information. So in this case, we only have one dummy variable, so basically that represents a qualitative variable with two categories. Let's assume that this is quantitative. That, of course, it could be generalized to the case where we have more dummy variables representing different categories, or having more than one dummy variable representing different qualitative variables. I think that this example provides us most of the intuition that we need. So the specific example is an example where we have wage, and this is the population model, and as a function of education in years, and also female. There's been a lot of discussion regarding the gap in wages between males and females. So it's interesting to see what happens with that gap if you control for the effect of education. And that's kind of the general context that we have here. So in our example, we have data $10 per hour. Education. This is years of schooling. And the units are years. And the dummy variable, so we have this dummy variable that represents a qualitative variable with two categories, so it's equal to one is female. Female, of course, equal to 0 if male. Okay, so using this data from the 70s, we have the estimated model as follows. 0.506 education minus 2.673 female, so that's the estimated model. So let's add also the standard errors underneath the coefficients. So the error square 6 and 5.6 F 1.02 divided by 2.01. Okay, so that's the estimated model. So let's practice interpreting the coefficients. So of course, the p-value for the F statistic is less than 0.05, which means that the model is useful for prediction. 26% of the variability in wages is explained both by education and gender. So that's it's not that high R-squared, but for cross-sectional data, actually, it's not that bad. So let's go ahead and let's interpret coefficients. So let's start with the intercept. Intercept 0.623. So in general, remember the intercept is the average value of the dependent variable when the explanatory variables are equal to 0. So in this case, so that would mean that the so that would be the average wage for somebody who has no education, and female equal to 0, that represents male. So that's the average value for a male with no education. Okay, so remember, we have female equal to 0, which that means that we have a male, and education is equal to 0. So here, you have to be a little bit careful, because actually female being equal to 0, it represents the group corresponding to males. So let's look at the other coefficients. So now the coefficient related to education, which is 0.506, 506, and so the interpretation would be that each additional year of education increases average wages by $0.506 per hour, ceteris paribus. Each additional year of education increases wages. Well, so I'm going to be complete. Since average wages by $0.506 per hour. Okay, ceteris paribus to be complete. So ceteris paribus in this context means controlling for other things. In this case, it would be controlling for gender. And the other coefficient is the coefficient corresponding to gender, to female, -0.273. Remember that is the coefficient corresponding to female, and the way that we interpret the dummy variables, always it's easier to think that this is the average value of the female category relative to the baseline, which is males. So we can say that relative to males, the average wage for females is $2.272 per hour. Okay, so that will be the interpretation. And again, so this should be ceteris paribus. Using this context, ceteris paribus means controlling for education. So even after controlling for education, we have this gap in the wages. Okay, so let's given this estimated model, something that doesn't seem very obvious by just looking at the equation is that when we estimate this equation, it's actually if we were estimating two different relationships or two different models, one model for males and one model for females. So let's see what happens if we plug in 1 and 0 in that estimated equation, you will see how we can come up with two different equations, estimated equations, one for males and one for females. Let's look at that. Given the estimated relationship, we can write separate models for males and females. Okay, so let's write the model for male. Let's start with the model for female. So what we're going to be doing is just going to plug in a 1 the estimated relation. I'm going to divide both relationships here. Female equal to 1. So if we go back to our model, we have 0.623, 0.546, this minus 2.273 times 1, 1.55, 0.56 equation. Okay, so that's the model for females, and we just plug in the 0. Similarly, we can say that we can write a model just for males. And remember, for males, female is equal to 0. That's the case. We have a male, so again, using our estimated relationship, we just plug in the number 0. So we just have 0.63 and 0.66. As you can see, basically, within the model that we had estimated, it's like if we had two different lines of the relationship wages in education, one for males and one for females. So let's graph those to compare how they look like. I'm going to use 0, 5, and 15 years of education. So wage is equal to minus 1.65 and 0.56 education. So if we were to plug in those values, because if it's 0, it's minus 1.65. If it's 5, you have to plug in minus 1.65 plus 0.565, 0.8, and 3.41. So the same thing, we can do the same thing for males. So we'll write the expression. Again, 0, 5, 15. So the weight is 0.023. If it's 0, if it's 5, 3.153. And you can do the math for that. So 15, 5.68. Again, so we have the equation, and now what I'm doing is I'm trying to plug in different values so that we can graph this relationship. That's it. Yeah, the way to think about it is like if we had estimated here, just the line I'm going to write. So let's start for males, 0, 0.625, Well, I'm going to write here 1, 2, 3, 4, 5, 6, 7, 3, 5, 6, 7, and 0, 5, 10, 15. Okay, so it's going to be that 0.623. 5, approximately 315. And for 10 and 15, 568. So that's going to be the line. It's supposed to be a line. Let's see. 5.67. Points. Okay, well, let me try it again. So that's 0.65, 5, 3, 5, and 15, almost 6. Okay, so that's slightly better. So that's the relationship, estimated relationships for male. Okay, and for female, the value of 0 is actually minus 1.65, which we know that doesn't make any sense. So remember, sometimes the intercept is not very meaningful. Okay, so this is the case here, so that's our value. Then we have for 5, 0.88. There. And for 15, 3.41. There. Okay. This is the wedges for female. So as you can see here, more or less, even though the graph is not perfect, so both equations, basically what they reflect is that two lines are parallel. So basically, from the graph, but also from the regression, you see the slope of the relationship between wages and education is the same, both for males and females, which basically means that the effect of an additional year of education is the same for males and females. Two notes here. So we have the same slope. For males and females, which basically means that the effect of an additional year of education additional year of education is the same for males and females. Okay, so that's important because remember, from a applied perspective, basically what we're finding is that the effect of the additional year of education is going to be the same both for males or females. And the other thing is then both curves are parallel. So both curves parallel, which basically means that the differences in wages for males and females is the same. Ceteris paribus. So the differences in wages for males and females is the same. Okay? And again, so what does ceteris paribus mean? And that's actually a good example because it allows us to see visually what this ceteris paribus means. So remember, ceteris paribus means fixing everything equal. So here, for example, we say that ceteris paribus because you see that difference between wages for males and females is the same if the male and the female that we're comparing have 15 years of education, or if it has 5, or if it has 0 years of education. So that's what it means, ceteris paribus, controlling for the other factor. It would be kind of, in a way, not fair to compare, the average wage for a female with only 5 years of education and a male with 15 years of education. So ceteris paribus means that we are controlling for these other factors. And again, and I have talked about this before, so regression in a way allows us to kind of artificially control for those other factors. So that once we have included all those variables in the regression, we can have this comparison that it's, in a way, is more, it's more fair to compare males and females that have the same level of education. So that's kind of what the concept of ceteris paribus means. So this example also help us to reinforce that concept. Okay, so the other thing, so as you can see here, from that very simple model that we have, a model with only one quantitative and qualitative variable. The way to think about it, it's a lot of information that actually we're being able to generate with this type of model. You see, from this model, we were able to draw 2 different models, one for males and one for females. So the other thing is just some additional information. So you see the differences in wages for males and females is the same. So sometimes, if you look at this graph, basically what we were doing with that dummy variables for male and females, what I was doing to the graph was shifting the curve, was shifting the intercept. You see, this is the intercept for females is minus 1.65 and for males 0.623. So they have kind of different intercepts. So sometimes if you read in the literature, sometimes dummy variables are called intercept shifters. Are called intercept shifters because it has that property of shifting the intercept. Now, some of you might be wondering, well, maybe, it would be interesting to try to estimate, a model where both not only the intercept but also the slope change. There are 2 ways to do that. One way would be just to separate the regression, the data, and run one regression for males and another one for females. The other way to do it would be to add what are called interaction terms, but that's a topic for probably for a graduate level class. So it's possible to do that. So the model that we have estimated, it has a lot of power, but some of you might think that somehow it's limited, because the effect of an additional year of education might be different for males or females. And that's not the model that we estimate. So that's one thing. The other thing is, I want you to be thinking about how will you go about interpreting the coefficients. So this is just 2 things. How would you go about interpreting coefficients, for example, of a model where you will have the log of wage saving. And as explanatory variables, we have education and female. Okay, so it's interesting for you to be thinking about how will you go about interpreting that data one and that data two coefficients. Just think about that. That would be an interesting example to have. And with that, we're done for today.